Okay, welcome. My name is Kevin Kahn. I am a senior at Cal State East Bay, and this is my fourth and final proof for senior seminar. And I'm not gonna lie, guys and girls, everybody watching, I just recorded this video and I forgot to unmute myself. So here we go. Take number two. We'll see if I can be as lively as take number one. I today here will prove let's go with we will prove that the real numbers are uncountable, which is just quite a wonderful proof. So our overview, we're gonna look through, have a quick review. The audience for this video is senior math majors in college. So this review should be actually very quick. And then we will show that decimal representations are not unique. We will ask the question, what is countable and what is uncountable? And based on what we get from those answers, we will look at examples. Still not that good at drawing on the iPad while not looking. After those examples, we will prove that the real numbers are uncountable. Let's get going. Review number 1 and 2. Cardinality is just the number of elements in a set. If we had a set A, B, C, D, that's 4. The cardinality is 4. Just the number of elements in a set. One-to-one function means that for a function going from set A to set B, all the elements in B have one element in A mapping to it. So you can see here on the bad one, we have 2 elements going to Z. That's not good. That's not one-to-one. Onto. Man, that joke in the last one was so much better. You guys will never get to hear it. Onto means that our set B is fully mapped. That's how I remember it. Basically, all the elements in B have something mapping to it. You can see here that this is not a one-to-one function, but since B is fully mapped, it is onto. The reason why this is bad is because we have Y hanging out here by himself or herself, themselves. No one is mapping to them. That is a problem. That's not one-to-one. That is bad. Well-defined is what makes a function, essentially, but we still need to kind of define it here. It's saying that an input only has one output. So A can't go to X and Y at the same time. That's a problem. That's not a well-defined function. So now we will look at decimals are not unique. So my claim is that 0.43999999 repeating is the same as 0.44. And you might be thinking to yourself, what is this guy smoking? I know it's April 20th, but you've got to be kidding me. These numbers are clearly not the same. I claim that they are. And to show you, to illustrate that they are the same, let's let A equal this 0.43999999 are repeating. Let's multiply both sides by 10. So let's pop that decimal over 1, and we have 10A. Let's take these two equations and subtract them. So 10A minus A is 9A, and 4.399999999 minus 0.43999999. In the first video, I crossed out these 9s because they just match up and take care of themselves. So we really have 4.39 minus 0.43, which is equal to 3.96. Do a little bit of algebra, divide by 9. A is equal to 0.44. So A is equal to 0.44, but then it's also equal to 0.44. So that means that my claim was right, and that this repeating 9 at the end of a decimal is the same as rounding it up. That's what we're going with. So again, decimal representations are not unique. We need this feature to we need to show this and mention this so we can make sure we don't have duplicates in our proof at the end when we show that the real numbers are uncountable. So what does it mean to be countable? That means that a bijection exists between your given set and the natural numbers. And if we recall, a bijection is a function that is surjective and injective. But since I can't remember which one is surjective and injective, I remember that a bijection is one-to-one and onto. That's why we reviewed it earlier, obviously. Just checking to make sure that this is recording and that the sound is on, so I don't have to do this for a third time. So to be countable, there is a bijection between the given set and the natural numbers. The natural numbers, of course, the counting numbers, 0, 1, 2, 3, 4, 5, 6, 7, blah, blah, blah. You can include 0 if you want. I'm going to include 0. You know what? No, I'm not including 0. So bijections are invertible. That means your function can be written like this or like this. So some examples. The set A, B, C, D, E, F. This is countable. This is finite. There are two types of countable. There are finite countable, like this right here. I mean, we clearly can very easily just count 1, 2, 3, 4, 5, 6. Countable, finite. No big deal. Sets like this, they can be bigger, but if they are finite, they are countable. And now you may be thinking, so if something is countable but not finite, what is it? It is infinite. That there represents the integers, the z. The integers, as well as the natural numbers, are infinite. It is crazy. We can call something countable in math, even if it would take you the rest of all human eternity to count the set itself. But hey, this is what we've decided. So the idea behind the function that brings f z into n is to map all of the odd number, or all of the negative numbers to the odd numbers, and all of the positive numbers to the even numbers, or vice versa, or what have you. But the idea is take one, break them down, take one set and match it to the odds, the other set match it to the evens. So even though these two sets are indeed infinite, they are both countable, which is a little bit weird to wrap your head around. But it's okay. So we're going to move right along here, kind of steaming on by. Hope everyone's okay with that. So we are going to get to this proof where I am claiming that the real numbers are uncountable. So we kind of talked about what it means to be countable. It's that there exists a bijection between a given set and the natural numbers, basically meaning that if we had infinite time, we can count your set. We can count this set. So to be uncountable, that must mean that there does not exists a bijection between a given set and the natural numbers. So that means that there's no way to accurately match up elements from a given set to the natural numbers. That's what it means to be uncountable. And there's only one type of uncountable. If you are uncountable, you are uncountably infinite. I gotta admit, I really like the fact that there's two types of infinite, countable and uncountable. Yeah, math is so crazy. So for this proof, we are going to go for a contradiction. We are going to assume for a contradiction that there is a function that takes inputs from the open interval of 0 to 1 and outputs them in the natural numbers. And the reason I am looking just at this interval is because even if I prove that this interval here is uncountable, that means all of the real numbers are uncountable. You cannot have a set, the real numbers, you can't have a set that is countable while a subset of that set is uncountable. That's impossible. You can go the other way around. You can have an uncountable set and take a subset that's countable, but you cannot have a set that is uncountable. You can't have a set that's countable and a uncountable subset of that. If the subset is uncountable, then the whole set is uncountable. So I'm going to prove that 0 to 1, the open interval from 0 to 1 is uncountable by a contradiction. So we assume that 0 to 1 is countable. So that means there is a function that takes every number in that interval and matches it with a natural number. So if we were looking at the function not this way, but the reverse, going from the naturals in, we could say that f of n equals this long string of decimals, or this long decimal string. So for every n in the natural numbers, the output of that function is in the interval from 0 to 1. And we can create an array that lists every single real number from 0 to 1, not including the endpoints. This array has no duplicates. There are no duplicates. That's why we went over the 0.43999 equals 0.44. We're ensuring that there's no hidden 0.5 and 0.4999999 in there. Those would be duplicates. We are ensuring there are not. And we are also saying that this array, which goes on forever because it is infinite, but countable. So this array that goes on forever contains every single number on the open interval from 0 to 1. Okay. The technique we're going to use to show that this assumption is incorrect is Cantor's diagonalization technique. We're going to look at that same array and we are going to create a new number. That number will be x. X will be 0.b1, b2, b3, b4, b5, b6, be real, be infinity. And we are going to let this be defined by bn we'll look at ANN. If ANN is a 4, that number will now be a 7. We will change that number into a 7 and add it to our x. If it is not a 4, we're going to make it a 4. So what this does is it goes, since a, n, n, these will be the same, so we're just going to move along this diagonal forever. And we are going to look at this. A11, are you a 4? You're not a 4. You're now a 4. A22, are you a 4? You are a 4. You're now a 7. A33, are you a 4? You are a 4. You're now a 7. A44, are you a 4? You aren't a 4. You're now a 4. This new number will be comprised made by going down this diagonal and hitting every single element in this list and saying, are you a 4? Or you can change these out. It doesn't have to be just 4s, but it is going to change every single element along this main diagonal for every single element in this infinite list. And when we are done with that, we will have a number x that is unique from every single number on the list because we went and changed one number. We made one number different than every number on the list. So we have a new number, x. But that's a problem. That's a contradiction because our assumption is that we already had every single real number on this list in the open interval from 0 to 1. So you might be thinking, okay, well, let's just add x to the list. Now we have everything. But then I change this to a 5 and this to a 2, and we do it again. And we keep adding numbers, and we keep finding numbers that weren't in the list, and we can repeat this process forever. So the assumption that there exists a bijection between the open interval 0 to 1 and the natural numbers is incorrect. That means that the open interval from 0 to 1 is uncountable. That also means that all of the real numbers are uncountable. Thank you very much for sticking it out to the end of this video. Let me make sure that I've hit all of them their homework questions that we're going to ask about. So, I don't know how long this is, probably not terribly long. What is the main contradiction achieved with the proof Cantor's diagonalization? I just mentioned what it was. Show that 0.999 is equivalent to 1. Here you go. Use this technique. It'll work. What does it mean for a set to be uncountable? It means that there does not exist a bijection between that set and the natural numbers. Describe or make a cool drawing on what it means for a function to be surjective. I don't know about you. I think that's a pretty cool drawing. You could make one that looks like it or not. It's your world. Anyway, thank you. Seriously, thank you for watching. I have enjoyed making these videos this semester. So on that note, signing off for senior seminar. Have a good rest of your day.